Hello there. This is a video on section 5.1, at least the first part of 5.1, where I'll be showing you how to estimate a quantity using rate data. All right, so I have a couple of examples here, and this is leading to a bigger idea in chapter 5 about areas and rates, and I'm going to give you a preview of how that works. All right, so my first example is a very straightforward one. It's this one right here, example A. It says a vehicle is traveling at a constant 50 meters per second. What distance did it travel after 10 seconds? So many of you may remember the distance equals quantity, rate times time, kind of thing like that. So that would be sort of rate times time equals distance. Or in general, anytime you have a rate times a time, you get a quantity. In this case, we have a rate which is 50 meters per second times the time, 10 seconds. And if you remember your algebra, 50 meters per second times 10 seconds gives you a total of 500 meters. And even without these formulas, you can kind of figure this out. During the first second, you traveled 50 meters. During the next second, you traveled 50 meters. You travel 50 meters each second. So total, you'd have 10 times 50 meters, right? So 50 meters per second literally means every 1 second I've gone 50 meters. After 10 seconds, you've gone 50 times 10 or 500 meters. All right, I'm going to show you a visual of this. It will come up quite a bit later, even though it seems a little bit strange at first. I have an axis here. On the vertical axis, which is the y-axis, I'm going to put the rate. So this is the rate, which in our example here is going to be meters per second. And in the horizontal direction, let me just clean this up a little bit. In the horizontal direction, I'm going to put the time, and that's going to be measured in seconds. So what do I have here? I have that originally at time zero, we have this vehicle traveling 50 meters per second. So I'll put 50 up there. So that's the rate at time zero. But the rate at time everything is actually 50. It says a constant 50. So at time one, it's 50. At time two, it's 50. At every time all the way to 10 seconds, it's going 50 meters per second. Uh, because it's going a constant, we know the rate doesn't change. So we could just connect these all with a straight line. Thus, we have a graphical image of a constant rate of 50 meters per second over 10 seconds. So we're multiplying this 50 meters per second times this 10 seconds. And if you remember your geometry, if you're multiplying 50, this right here, times, well, I guess here or here, I'll do it down here, times 10, right? The 50 here times the 10 here gives us the area of this box. And mathematicians will call this the area under the green, under the output variable, out under the rate. So you find this area, 50 times 10 is 500. So this is 500 meters. Now we're usually thinking of like the units of area being like square meters or square something. But that's just a physical dimension, like meters times meters, square meters. Here, remember, we have meters per second times seconds. So our area is actually measuring a quantity of meters, 500 meters, the distance, in fact. Okay, so that's our basic example. Let's step it up a little bit on example B. Example B, we have a vehicle again. It starts from 0 meters per second and steadily speeds up to 50 meters per second over 10 seconds. So let me draw my picture again. It's a similar picture, but we're starting off at 0. So we're starting off, well, let me put this vertical axis as rate just to remind you. This is our rate, which is meters per second. And this is our time, which is seconds. So at time 0, it says we're going 0 meters per second. So we start off here at time 0, and eventually we get to 50 meters per second over 10 seconds. So over 10 seconds, it's back up to 50. And it says it's steady. So it steadily increases over time. So we can try to figure out what it is at 1. That would be, whatever we could figure out the slope. That seems to be 5, because 50 over 10 is 5. So we know it went up 5 meters per second over that 1 second period. And we could sort of see that visually. It's actually not that important for us to do so, because once again, we know that if we multiply the rate times the time, we get the quantity. In this case, we have this rate goes from 0 to 50. So it's not a constant rate. We do have over 10, and we get a picture of a triangle. So what's the area of the triangle? Well, it's 1/2 times the base times the height, which in our case, the base is 10 seconds, and the height is 50 meters per second. So let me get a little more space here. Let me just write a little bit larger so people can see it more easily. So we get 1/2 times the, which is 10 seconds, times the height, which is 50 meters per second. This is the same kind of thing, but I've reversed the order. Instead of 50 meters per second times 10, I switched it around just because of the way the formula in geometry is usually memorized. Nonetheless, it's still 1/2 of the 50 times 10, which is 1/2 times 500. Notice once again, we have seconds and meters per second, simplifying to just be meters. And so we get a grand total of 250 meters. So we have a vehicle starting at 0 and steadily increases. That means they've gone half the distance that they would normally have gone. And that's in fact what we have. We had 500 meters per second when they were going constantly. And here they've sped up slowly over time at a constant rate. And so we get 250 meters as the distance they've traveled during those 10 seconds. So once again, we're trying to connect the area of this sort of situation to the quantity. You can kind of see, if I kind of overlay this here, right here, this giant green kind of box, that's the 500, right? That's the constant rate of 50, and ours is just this little half piece right here. That's the 250, right? That's the 250 meters that we went. We do this way. Right. So visually, hopefully you're seeing that if we can calculate the area under this rate graph above the x-axis, we can find the quantity of that during that time period. All right, so let's see something a little bit more, maybe more interesting than these simple examples. Okay, so let me zoom in here. I got a couple more examples for us, and then that will be it for this video. Okay. We have here some data that was collected about the velocity over a certain number of times. And we have at time 0, we know the rate here was 10 miles per hour, and we're given some additional rates. And we want to find the distance traveled. Now, we don't have enough information to know the exact distance traveled, because we aren't told anything like the last time that we had a constant rate or a constant increase. It just says that it was going these rates at these times. In between, like in between 0 and 1, we don't know that it steadily went from 10 to 30, or if it sped up close to 30 really fast and then slowed off or steadied off to be 30, or whatever version of this. So we do only get an approximation But this again is serving a bigger purpose. If you want to get a visual of what's going on here, I'll just draw a little graph here. The rate is going to be on the vertical axis. The rate in this case is measured in miles per hour. Miles per hour. It says M, but that's going to stand for miles in this problem. And we have a time over here, and that's going to be in hours. And then we're going to put in some numbers here. We go from 0 to 10. So I'll put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be a sketch. Don't worry about it being precise. The rate goes from 0 to 100. So I'll just count by tens as well. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So that is just a rough sketch just to give people a visual of what's going on here. At time 0, we know that this vehicle, or at least the velocity, is at 10. At time 1, it's 30. At time 3, we don't know anything about time 2, but at time 3, we know it's 40. Let's see, 3, 4, 5. This is 6. At time 6, it's 50. Time 6, 7, 8, it's 80. And at time 10, it is all the way to 100. I'm going to move over here. Okay. So we do know that these are the time elements. We don't know exactly how these are connected, if they're connected at a steady rate, steady growth like this, or maybe they ramped up a little bit, or maybe they sped up really fast and then leveled off. It doesn't really matter. We're only getting an approximation. So what we're going to be looking at here is an approximation for the area that somehow connects these dots. I don't really know that it's a straight line, but we're going to do our best, or connected like that, but we're going to do our best to figure out the area. We do know in this first time element that this is the lowest speed and this is the highest speed. Or at least we're assuming that. So in this little picture here, 0 and 1 and 10 and 30, in that first sort of like time interval that I've sort of made a bigger drawing of here, we know that this distance traveled was a minimum of 10 over that 1 second, but it could have been as much as 30 over that 1 second. So we have sort of a minimum approximation and a maximum approximation. We call it an upper estimate and a lower estimate for the quantity over that time period. So we're going to be perhaps finding different estimates for these: upper estimate, lower estimate. We'll even do something called a midpoint estimate. Later on, we won't need all these estimates, but this is sort of building the idea of what's going on so that it's not just a random formula we throw at you. It has some meaning of what's going on here. So we're going to find the lower estimate. And then we're going to find the upper estimate. And afterwards, I'll talk about what a midpoint estimate is. All right, so for the lower estimate, during this first time interval, if you remember, I said that we're going a minimum of 10 miles per hour. So 10 miles per hour over 1 hour would give me this little shape right here. So a lower estimate would be sort of 10 times 1, 10 miles per hour times 1 hour. I mean, right in the units there, just so you can see those. 10 miles per hour times 1 hour would give us give us 10 miles as our approximation for that first time interval. But what about the next time interval? Next time interval goes from 1 to 3. So from here to here. And again, we have a lower estimate for the rate and a higher estimate for the rate. The lower estimate is going to be the lower of these two numbers, which is 30. And the higher estimate is going to be the upper estimate is going to be the higher of those two numbers, which is 40. So for the second interval, the lower estimate is going to be 30, the lower of the rate. times the time interval. Notice we're going from 1 to 3, so that time interval is 2 hours. Over the next interval right here, it's from 3 to 6. The lower estimate is 40, and that's over a 3-hour period. And we're going to continue doing this, each time finding the lower estimate. And it looks like I'm a little bit out of space. So the last one here is lower estimate of 80, and that's over a 2-hour time period. Likewise, the upper estimate is going to be the same kind of thing, but on the first time interval, we're going to take the larger of the two rates as our estimate, upper estimate. So this is going to be 30 times the same 1 hour. And then the second interval, we're going to be 40 times a 2-hour interval. And we're going to continue on finding an upper estimate for each of those time intervals. So 50 times 3, 80 is the upper one, and that's over a 2-hour estimate. Let me make sure I do this right. Plus 80 over a 2-hour interval. And the last one is the maximum of 100 over a 2-hour interval. All right. Yeah, I think I did it right. So we need to add these up. I've actually done the little calculations in Desmos already. So this lower estimate is 10 times 1 plus 30 times 2 plus 40 times 3. And that should be up here at the top, right here. 10 times 1 plus 30 times 2 plus 40. So I typed it in so to save a little time with you watching me do calculations. So we got a total of 450. So our upper estimate is 450 approximately. 450 watts is the question. So 450. Pen stopped working, so let me just pause the video and see if I can get my pen working again. Okay, so we get a total of 450 watts. Remember, we're multiplying the miles per hour times hours, so we're going to get miles. The first one's going to be a total of 10 miles. Then we have 60 miles, grand total of 450 miles. So that's our lower estimate. The upper estimate, we just do a similar calculation, and that ended up being this one, 30 times 1, for a total of 620. So that's our upper estimate. So what's this midpoint estimate? Well, we can try to do a little bit better than just take the lower amount of rate or the higher amount of rate. So in this time interval, in the first time interval that I've sort of made a little bit larger here, we notice that it's somewhere between 10 and 30. The lowest is 10 and the highest is 30. So why don't we just take the average, right? So between 10 and 30 is around 20, right? You can take 10 plus 30 and divide by 2, and that would be the middle y value. What we're really doing is taking the middle of the time interval, so between 0 and 1.5, and we're trying to estimate the value up here, right? So the value at that interval time of 1/2 is around 20. If we kind of think of this as a gradual increase, I know it may not be, but again, we're just estimating the midpoint. So if we estimate sort of halfway between 0 and 1 that the rate was 20, then we get 20 as our rate times, now it's still 1 because we still have a time interval of 1. So I know I put a half in there, but remember that time interval is 1 hour in length, and the average rate is around 20. So the time interval lengths aren't going to change no matter how we estimate the rate during that time interval. In the second time interval, we are between 30 and 40. So the average of that would be like 35 over the 2-hour period, etc. So we can do the estimate for each of these time intervals, and that would give us a midpoint estimate. Between 50 and 60 is 65, I believe. And between 80 and 100 is 90. and that's over a 2-hour interval as well. All right, and then I did this before in Desmos, and that gives me 535. So 535 is our midpoint estimate. And just for you to sort of have a bigger picture, we are taking the middle of the two rates each time. So you would imagine that the middle is sort of like the average. And indeed, if you take the lower estimate and you take the upper estimate and you average them together, you get the midpoint estimate. So I'll show you that over here on Desmos. Here's the lower estimate of 450. Here's the upper estimate of 620. I added up and divided by 2, and I got the same 535 that we got before in the midpoint. So that's sort of an improved estimate by averaging together the upper estimate and the lower estimate. All right, so that's the idea behind sort of using this rectangular approximation, using this area, using this data, which is about rates to approximate a quantity. Now, there's nothing special about like distance and time, as long as you have any rate times the quantity. So as long as you have or any rate times the time. So you have any rate times the time, then you're going to get a quantity, as long as the time matches the rate. It doesn't have to be this. In this last example right here, you notice that I do have time in minutes, but my rate is not in meters per second or meters per minute, or not miles per hour or miles per minute. It's cubic feet per minute, right? So what the heck is going on here? Well, the information says, or the problem says, the data below shows the inflation rate of a balloon at different times. So it's how much volume of air is being pumped into this balloon at various times. So in the very beginning, when we start our pump, we have 70 cubic feet per minute being pumped into this balloon, and it decreases over time the rate. So we have different rates depending on how long we've been pumping up this balloon. And we're supposed to approximate the total volume. Again, our rate is cubic feet per minute. Our time is in minutes. If you multiply cubic feet per minute times minutes, you get cubic feet. And cubic feet is volume. It's a measurement of volume. All right, so I'm going to invite you once again to see if you can come up with a lower estimate, upper estimate, midpoint estimate. I'm going to pause the video and write out my answer, and then you can check to see if you did it correctly and have the same results as I do. See if I did it correctly. And hopefully this will be a good experience to end our video with today about estimating a quantity given rate data. All right, so hopefully you had a chance to try that yourself. I have my work here, my calculations for the lower, upper, and midpoint estimates. And you could check to see if you have the same calculations. The results are 350 cubic feet for the lower estimate of the volume, 500 cubic feet for the upper estimate of the volume, and 425 cubic feet if I use the middle of those two quantities, those two rates, excuse me, to calculate the quantity. And I also did check that the average of the lower and the upper is in fact the same as the midpoint. All right, so this was the video on approximating or calculating a quantity given some rate data, some numbers about the rate. We can use that to either calculate or approximate more generally the quantity. So hopefully this was helpful for you, and please do reach out if you have any questions. And I also hope you have an enjoyable day.